Hi everyone, I'd like to wrap up this module on electromagnetism and make a connection between some of the different things we've been talking about throughout the year and then finally the last module on optics. So to review some of the big discoveries we've talked about with electromagnetism is that electric current will give you a magnetic field. This is known as Ampere's law. And discovery 1A, also related to this, is that a moving charge or a current that interact with a magnetic field will undergo a force known as the Lorenz Force. This gives you an electromagnet that you can control and also electric motors. The next logical step is to ask, hey, if electric current gives you magnetic field, can I reverse the arrow and get a magnetic field to give you current? And the answer is no, not directly. But what we can do is change magnetic flux. So if we change any of the variables here, magnetic field, area of a loop of wire, or the orientation, we can create an EMF or a current. You can create an electric generator by changing the magnetic flux. So electromagnets, electric motors, and then finally electric generators. So a couple of really important practical discoveries. The final discovery, the final big discovery number 3, is this: light is an electromagnetic wave. And so over the next video or so, I want to try and describe how do we make this connection. The first step to develop the idea that electromagnetic waves and light are the same thing are to remind you this relationship between waves and oscillations that we talked about in the beginning of the course. You need an oscillating system to both generate and receive waves. So in the case of sound, you need something like a vibrating drum head or a guitar string to make a sound wave. And then you also need the oscillating system of your eardrum and some tiny bones to receive the sound wave. They have to shake at a certain rate. Another thing to remind you about is that an oscillating system not only oscillates between positions, but also forms of energy. So here we look at the sort of two classic oscillators, mass on a spring. So we have a mass on a spring. So here I've got a spring and a set of keys. Get my hand out of the way here. And they bounce at a certain rate. The frequency of oscillation depends on the spring and the mass. The other kind of classical mechanical oscillation is a pendulum, and so that depends on G, what's the gravitational field, and the length of the pendulum. That works for small angles. It gets a little bit more complicated at bigger angles, as you have already seen. The other thing to mention is that these are both resonant frequencies or natural frequencies of oscillation that depend on the system. And so if you drive a resonance, if you push a kid on a swing at a certain rate, the amplitude will shoot way up. Try to do the same thing with the keys here. If I bounce at a certain rate, you can see that the amplitude goes nuts. Another classic demonstration of this is the idea of shattering a wine glass with your voice. In looking at electric systems, an oscillating system is what's called the Rlc circuit. So here we have a capacitor and an inductor. Let me give the inductor the variable L. Capacitor is just two plates with a gap between it, and then an inductor is just simply a coil of wire. And as we'll see in the next couple of slides, what happens is that you can make this an oscillating system with charges and currents. The oscillation is related to the inductance and the capacitance.